It's April 15th, and this is the recap video by Dakota, Adam, Kang, and Megan. To begin lecture on Friday, Professor Free described our third and last exam that is this upcoming Friday, April 19th. It will be an in-class 50-minute exam and will cover material through April 12th. The exam, like the previous two, is closed notes and closed book. However, a formula sheet will be provided and has already been uploaded to Blackboard. Also, practice problems and all homework solutions have also already been uploaded to Blackboard. One thing to note when studying is that no orbital equations are included on the formula sheet.
Previously, we found that the analytic solutions to the Euler equation for a symmetric body are omega x of t equals omega x naught cosine lambda t minus omega y naught sine lambda t, and omega y of t equals omega y naught cosine lambda t plus omega x naught sine lambda t. Squaring both of these equations shows that omega x squared plus omega y squared is equal to omega x naught squared plus omega y naught squared, which is a constant. We know that omega z of t is a constant, capital Omega, and that the omega vector is omega x of t plus omega y of t plus omega z of t. Putting all of this together, we see that the magnitude of omega is the square root of omega x naught squared plus omega y naught squared plus capital Omega squared, which is a constant.
These analytic solutions for omega x, omega y, and omega z allow us to sketch the angular velocity vector in the body frame as seen in figure 737. The vector omega xy of t rotates at a rate of lambda radians per second about the b3 axis and is constant. The total angular velocity vector creates a body cone as it rotates around the b3 axis. By considering these equations of motion and assuming lambda to be positive, we can show the direction of motion to be counterclockwise about b3 as seen in figure 738.
Now let's look at the angular momentum for the same symmetric torque-free rigid body. The picture on the left is a visual representation of the angular momentum in the body frame. Because the rigid body is torque-free, using Euler's law, the moment equals to the derivative of angular momentum equals to 0. We can easily obtain that the angular momentum is constant in inertial space. However, in the body frame, we can only obtain that the magnitude of angular momentum is constant. By representing the angular momentum in the body frame, we can see it lies in the plane created by omega xy and b3. We can also observe that the angle between angular momentum and b3 axis is constant.